Now, informal definition, that we say that the critical point at the origin is asymptotically stable if all trajectories they kind of converge to the origin, stable if trajectories rotate around the origin, and unstable if they go away from the origin. Okay, and a challenge for you is to come up with a rigorous definition like that they do in real analysis. So what we have essentially proved is that a homogeneous system of linear differential equations with constant coefficients, right? So with a non-degenerate matrix, non-singular matrix. Well, it always has the critical point at the origin. So then the critical point at the origin is asymptotically stable if only if the real part of every eigenvalue is negative. Stable if and only if the real part of every eigenvalue is non-positive. And unstable if and only if there is some eigenvalue with a positive real part. So if that happens, then there will be solutions. There will be one eigenvector and the corresponding solution that is going to go away from the origin. And I suggest that you try to analyze all the theorems that we have gone through and figure out what remains unproved in this theorem. Right? So because I wrote that we have almost proved it. So what is still not proved? So this situation when we have spirals going away from the origin is called an unstable spiral point or a spiral source. So here is an example. And a spiral source can be sort of diagnosed by doing the following observation. So first, we look at the discriminant of the characteristic polynomial, so which is square of the trace minus 4 times the determinant, right? So the reason is because the characteristic polynomial of a 2 by 2 matrix is always r square minus trace a times r plus determinant a. So that's the characteristic polynomial. By observing that it has negative discriminant, we conclude that eigenvalues are complex. But at the same time, trace is still going to be the sum of the two eigenvalues if it is positive. And if so, remember that eigenvalues, they always come in pairs of conjugates, right? So if they are complex, then one of them is going to be, r plus I mu, and the other one is going to be r minus I mu. But if you add them together, then the imaginary part is going to cancel out. So trace is just 2r. So if trace is positive, so then r itself is always positive, also positive. And the magnitude of the determinant, well, a bit informally shows how fast these spirals rotate. So here is an example. Well, it's not a very rigorous statement, so to say, but here is an example of what I mean. So the bigger the determinant in magnitude, it means that as compared, the imaginary part of the eigenvalue is bigger as compared to the real part, and then which shows that within the same period of time, the spirals kind of go more times about the origin. So the opposite situation is when everything converges towards the origin. It's called a asymptotically stable spiral point or a spiral sink. And it's very similar. The only difference is that now we can conclude that the origin is a spiral sink if we just see that first that the discriminant of the characteristic polynomial is negative, so then it means that the eigenvalues are complex. And then if the trace is negative at the same time, then we conclude that the critical point is asymptotically stable. And then same kind of observation that bigger determinant of A means that the imaginary part of the complex eigenvalue it has more weight as compared to the real part, well, informally, and then the spirals are going to do more kind of rotate around the origin more frequently. Well, and finally, it is of course possible if the trace of the matrix is 0. So when the element in the left top corner is exactly negative of the element in the right bottom corner. So, and then if we say that, it means that we have a center. But so don't forget that we at the same time we must have this. So here it is a bit. The trace is 0, so it means that this is not here. So minus 4 times determinant is negative. So in other words, center happens if the trace is 0 and the determinant of A is positive. Well, which basically means that these and these two elements, they have opposite signs. So one of them is positive, the other one is negative. Anyway, so here are these centers. They have kind of similar, same eigenvalues, but the systems that they come from, they're different in the sense that there are different eigenvectors. So the one on the right is a bit more round, but again, I'm not going to go into any further details about how to analyze this kind of information. So you can conclude that it's a center by just looking at the coefficients of the matrix, and you can easily produce the phase portrait by just by plotting it in MATLAB, and that